so here double integrals over rectangles, so this is the extension from the univariate case. So basically, in univariate case, we have one variable function, right? We have a single integral over a interval, right? Which is a closed interval from A to B, let's say. So let's quickly recall how we define that integral in Calc 1. Recall. Definite interval, right? So basically, this is the integral from A to B of a function f of x. And now, in the notation here, there's a dx, okay? So basically, this, if you assume that f of x is non-negative within this interval, then the above integral is the area under the curve, right? And the curve here is y equals to f of x. And now here we do have the restriction that the x value is between a and b. And basically, if you recall, this f of x represents the height of the bar, and dx represents the tiny little increment of the width, right? So let's say the function is like this. We have the axes, we have a and b. The function is y equal to f of x. And then the integral here represents the area that's cut between the top curve and the x-axis, and also between the dashed vertical lines, right? Area under the curve. And then, so that f of x is actually the vertical. So I'm drawing a strip right here, right? That's in purple. And then f of x represents the height, and dx represents the tiny little width, right? And then here integrating, this thing is actually integrating vertical bars covering the region. So if you really subdivide this interval from A to B into pieces, then that's actually the Riemann sum definition, okay? So the geometric point of view, from Riemann sum, so let's think about what we have been doing for the Riemann sum. So basically, if we don't really know how to calculate the interval or the area under the curve, what we can do is that we subdivide the interval from A to B into pieces. And let me reuse this figure. And here, we just subdivide the interval from A to B, right? So what do we do? So basically, divide the interval, closed interval from A to B to, we can use n equal pieces, okay? So actually, to do the subdivision, you don't really need equal pieces. But then you can make this choice. N equal with equal width intervals. So basically, what we do is that we call the value a on the left hand point to be x0, and then we have x1, x2, all the way up. And so if we are using n pieces, then b is actually xn. Okay, so x1 is the right hand point of the first subinterval, x2 is the second is the right endpoint of the second interval, and xn is the right endpoint of the nth interval, right? So that tells you x1 minus a is the width of the subinterval and the same as x2 minus x1. And finally, xn minus xn minus 1 is the same width. Okay? And usually they call the width to be delta x of the subinterval. Right? All right, now we do the subdivision, and then what we do is we draw the vertical lines up, and then this breaks this figure into pieces of equal width, okay, something like this. And then what do? So if you recall, we utilize, so basically the width is delta x, right? But then for every strip, let's say this piece, so when we do Riemann sum, you can choose the midpoint to give you the estimation of the height, or you can utilize whatever sample point. Okay? So here, let's just choose one. Let's say this is the first sample point in the first interval x1 star, and it has a y value to be f of x1 star. Okay? So if we use this height to represent the height of a rectangle, then that's exactly this region. Okay? That's approximating the area under the curve within on the subinterval. Okay? So I'm going to put it in red. Okay. So this area of the rectangle is fx1 star, the sample functional value multiplying by the width, right? And basically, what we do is we just repeat the process for every sub strip, right? And then we just sum up. Okay? Area of n rectangles is going to be the summation where I is the index, which represents the number of the counter of the rectangle, right? So basically, for every rectangle, it's going to be the sample point xi star within the ith interval multiplying by the width. Okay. So that's the definition of the Riemann sum when we use n rectangles. And of course, the more rectangles that we use, then the sample points are not essential. Okay. So here, xi star is any sample point in the ith subinterval. Xi minus 1 xi. Here I is from 1 to n. Okay. So then this is an approximation, right? The area under the curve between A and B is approximated by this Riemann sum. But then we can make n goes to infinity. Okay, so this is that basically using the fact that the more subdivisions that we use, the better the approximation will be. Okay? the symmetry function is continuous. As n increases, the approximation becomes more accurate. And then we take the limit where n goes to infinity. And the definition of the definition. So the integral from a to b of the function f of x dx equals to the limit when the number of subdivisions approaches infinity of the real sum. Okay. And you see that the definition of the definite integral has the form that's really the form of the Riemann sum, right? That integration symbol actually replaces the summation here. And then f of x just replaces the functional value at the sample point, and dx just replaces that delta x. Right. Okay, so this is a quick review about the definition of the definite integral for a univariate function on an integral, right? But now, in this section, we're talking about a bivariate function f of xy that is defined on a rectangle. So here we're gonna do the similar step. So basically, we subdivide the domain, which is subdividing a rectangle. And then on each sub-interval, on each sub-rectangle, we're going to utilize a sample point to approximate the height of a bar. So let's sketch a figure. So let us consider. So once again, we're going to utilize f of xy to be a non-negative function. Okay, so non-negative, so it's going to be a surface, right? Actually, it's going to be a curvy surface that's defined on a rectangle. So the surface is on the top, and then we're defining it on the rectangle. So we just have something like this. Okay. And here, let's introduce the axes. So we have the horizontal axis, we have the axis from the, well, a little bit parallel to the dashed line. That's the x-axis, y-axis. The height is the z-axis. Okay, so here, the definition of the box, okay, is actually the domain is actually a rectangle. So the x value is cut between these two values. So I'm going to extend these front and back edges. Okay, so that's the interval from for x is from a to b. Okay, and similarly for y, it's going to start from c and end at d. So that's c and d. Okay. And here we know that the region at the bottom is actually a rectangle. So that's what we know. So what are we looking at? We're looking at the surface at the top, z equals to f of xy. Here we have the region R to be the rectangle that has x between a and b and y between c and d. So to be more specific, that have R be in the domain which is AB cross CD. Okay, let me write down the set before I let you XY. So here, this is all the XY pairs within the XY plane, two-dimensional plane, where my X value is between A and B, my Y value is between C and D. Okay, so here, this R is a rectangle on the XY plane. So our question here is, what is the volume of the solid that's above R and below the surface? So, if you think about what we have done for the definite integral, that's going to be a two-step process. Firstly, we subdivide the domain, right? And then for every subdivision, there's a bar, there's a strip, and then we're gonna calculate the area as an approximation, and we sum up. So that's actually going to be the similar process here. So we subdivide the region first. And then for every subdivision, it's gonna be a bar vertically up, and then we also estimate the volume, and then we add up. Okay. So approximate. Direct, angular. Boxes. Well, we mean here the boxes mean we mean the three-dimensional. So subdivide the region first. So now looking at the XY plane, it's going to be X between interval AB, Y is between another interval from C to D, but then the region is this one, which is exactly a rectangle. So this is the base. So now we have two variables, X and Y. So we can choose to divide from A to B to n pieces. So you're going to have x1, x2, all the way up to xn, x0. But then from C to D, you can choose another number of subintervals. So you can choose to be y1, y2, and all the way up to yn. So this is n subdivisions, subintervals of AB. And here we have m subintervals of C. So here, let me put this text also here, divide to n times n sub rectangles where our delta x is, the changing x is just e minus a over n, right? And delta y is just e minus c over n. Okay. And now, so let me just quickly mention, basically you just subdivide, and then what do we do? So in the previous one-dimensional case, in every interval, you pick a sample, right? But here we just randomly, you can say randomly, or you can just pick midpoint, or you can just pick the like the lower left corner or whatever, but just a sample point in each subdivision. That would be good. Okay. So we subdivide. So if you want to thoroughly subdivide everything, it's gonna be still the same process. Then you're just gonna pick points. Okay, so that will be those will be the points of estimation, and they are called x sub I j star y sub I j star. So xi star yi star, these are really standard notation, but then the index ij, so there are two indices, because you need to think about which row you're at, which column you're at. So that's exactly what. So this is really like a matrix. But then we have what? We have m rows and n columns. So that's the only difference from the one dimensional case. And now let's estimate the volume. So it's going to be another figure. And now we think about each rectangular region at the bottom. So if you look at, let's say if you look at this one, so there will be m times n of those, right? But we need to choose a particular one, and then we're gonna cut this solid into m times n pieces. Okay? And every piece we want to estimate the height. And how do we do that? So if you do that, let's see. It's actually, if you really look at the way that we're describing this rectangle, it's actually somewhere here. It's actually near the lower left corner, and then in the XY space is somewhere like that. Then, since we're cutting vertically, we're gonna cut it all the way up. So the surface, there's gonna be an intersection, which is something like this. So this is a sub rectangle. And then we just need a height, right? So basically, the base, the area is actually not difficult to find. So if you really think about this, so we're gonna draw another illustration that is not that tall, not as tall, but we're gonna estimate the solid in red as a rectangle. Because if you have a general shape solid, it's just difficult to compute, right? So we just have to estimate. So it's so here along the y-axis is going to be delta y, that we have given the expression a little earlier, and then for the direction along the x-axis it's going to be delta x, right? And then like we said earlier, we just use any point. I'm going to put it in black. That's going to be that point xij star, yij star. So here, this rectangle right here, we are trying to estimate the volume of that long solid on the right. Right? The shape of that solid is not really rectangle, but here we're just going to use a height that's generated from that sample point. So this height is actually f of, and put in black, f of xij star, yij star. Okay. So the volume here is delta x delta y. So width times length times height. With this output here is a sample height. But then this you can also write it as what? As the height times the area of the base. And we use delta A to be the area of the base. So delta A equals delta x delta y. This is the area And it turns out that here, in this situation, we have a rectangle in the base. But if you subdivide it into other shapes like triangles, that's why we make a delta A here, delta cap A here. And then, of course, now I have given the way to estimate, but then still I want to illustrate this in the figure. Yeah, let me move this point a little bit because this point is too close to that shaded black dashed line at the back. So let me move it. Okay, let me also draw it out. So because I do want the height, right? So I want to do a dashed line all the way when I hit the surface. Okay, so that will be the height that I'm estimating. So this point in black, this is exactly xij star, yij star. So these are the xy coordinates, which is exactly the same as the bottom. So yeah, let me also label this here. The z value is 0. But now for the exact point on the surface, it's going to be f of x ij star. And I need a bracket. So this is a couple. Okay. Right. And now, here, this is just given any one of the m times n, right? Vertical solids, we estimate each one like this, okay? And then what we're going to do, we're going to sum up, okay? We're going to sum up and we take the limit. Okay? So approximated volume of the solid is going to be the summation of all n times m of those. And here we have I going from 1 to n and j going from 1 to n. Here is going to be the height times the base, okay? Area of the base. And you see, this is actually a double summation. Okay? So we're going to sum up every row, and then we're going to sum up every column. And now, if you think about this summation, earlier we had a summation. We have only one summation. Okay? We developed the interval from A to B. So one summation, it will turn into one interval. And so now, now we have two summations. That means we will have we have two intervals. As m and n increase, the approximation becomes more accurate. And of course, if we take the limit, if it converges, we are great. Okay, that's great. It's gonna be the exact volume. Definition. So now we're going to introduce a double integral over the region R. So you see here our region R is actually a rectangle, but we have double integrals involved. F of xy exactly copies from this piece. Okay. But then delta A is not delta A anymore, it's just Cn. Similar to delta x converted to dx. And here, this is exactly the limit when you push m and n. And here, you are taking the limit of the Riemann cell. delta. So this is the definition of the double integral. And then this is, you can see, really similar. So really similar to the multivariable case. So especially for the notation, this is a functional value, which is the height. Okay. That's going to be f of x. And this delta A is representing what? It's representing the area of the base, so it becomes dA. So that's also representing the area of the base. And then the two summations become a double integral symbol. But here we are expressing this as the region R at the bottom. So that's probably in a slightly. Right. Remark. If f of xy is non-negative, then the volume of the solid that lies above rectangle R and below surface z equals f of xy is exactly so. V equals double integral over the region R of a function f of xy dA. And put it in the notes. Right. So currently, we just established the double integral in terms of the definition, and it's the limit definition. So although we still don't really have a perfect way, nice way to simply calculate it, but still, the Riemann sum is actually a really nice way. It's a well-defined way to establish this kind of new problem. So given the Riemann sum, this kind of definition, we have a few properties I'm going to mention that you definitely need to keep in mind. But that's really similar to what you have seen from Calc 1. So they shouldn't look really new. So the integral properties. So if you have the double integral of the region R of a function of a sum of functions. So similar to Calc 1, the integral of a sum of functions is just going to be the sum of individual integrals. And then if you have a scalar multiplication, that scalar can be dragged out. And then if you know that one of the function is lower bounded by the other, for all points within the rectangle, then the integral is also going to be lower bounded. So these are really standard, right? So the parallel versions are already seen in Calc 1. And these can be all I would say easily or straightforwardly derived just by the definition of the roots. Okay, so now let's look at an example of how we're going to compute this example. So the first idea is that if you have this kind of if you have a cylindrical kind of shape, then it's always not difficult to just calculate the area of the base times the height. Okay, now let's think about this region R, which is -1, 1 cross -2, 2. So we just have x value, the x value between -1 and 1, y values between -2 and 2. So this is exactly all the pairs in the two-dimensional space such that x is between -1 and 1, y is between -2 and 2. And now we have the region. So we want to find the double integral on this region of 1 minus x squared under the square root. Yeah. So now think about this relation. So here we have the function, if you call it a z, and this is square root of 1 minus x squared. So there's no y here. So that basically means regardless of the y value, the z value is always the same. So now if you put it in the xz plane, regardless of the y value, then this is actually what the z actually equals 1 minus x squared under the square root. So if you look at this, this looks to be the upper half of the unit circle in the y in the x. So, and this is regardless of the z of the y value. So if we want to draw the surface, z equals square root of 1 minus x squared, it's going to have a cylindrical shape. Graph of z equals square root of 1 minus x squared in R3. So now let me. So let me think. So now, if we put the z-axis in this direction, x-axis in this direction, and y-axis in this direction, then you will see what. So when let's say if you fix y to be 0, then you will have what? You have a semicircle, but it's like this. And then whatever y value, the shape is always going to be the same, right? So if you put y equal to, let's say the maximum value is 2. So if you have y equal to 2, let's say it's here, then it's still the same thing. And if you have y as negative, it's negative 2. So if I draw it, then the shape that definitely will not look so great like if I draw it like this, but you get it. So, and everything is the identical shape. It's going to be like a shifting. And the top goes like this. That's the axis here. That's the axis. This is the origin. So this surface at the top, this is z equals 1 minus x squared. Excuse me, the square root of 1 minus x squared. So once again, so whatever y value that you fix, it's always going to be a semicircle. It's always going to be a semicircle. So if you think about this, if you say, okay, if I have the base to be the rectangle and I look at the surface, it looks relatively complicated. But then this essentially is a cylindrical kind of shape. So if you look at the let me show you on this monitor. So if you treat this semicircle as a base, then you can directly just calculate by the base times the height. And the height here is 4. And you just need to calculate the area of the semicircle. That's actually a relatively straightforward way to calculate this volume. So you don't need to do any integrals in this sense, although the question is asking you to calculate it that way. So let me write it down. Thus, the double integral that we are looking for is the volume of the cylinder and so simply put it on the right, it's going to be cylindrical shape. Right, the the width here, we can say the length is actually 2 minus -2, which is 4. Okay. So 2 comes from the maximum of the y band that we have in this region R, and the -2 comes from the smallest y band possible. And now, if you think about the area of base, so it's actually a semicircle. So you just calculate the circle, the area of the circle, and divide by 2, right? And then it all relates to the radius, and the radius turns out to be 1 in this case. So if you really think about this this point, this is 1. This x and this x is 1, z is x also. So the radius, so this is 1/2 pi r squared. So the integral is the volume of the cylinder in red above. So that means you can just write out the product. It's going to be the area of the base times the height, which is 200. So if I seriously want to label the numbers, I'm going to say this is 1, this is 1, this is 2, this is -2, 5 values. That will be clearer. Right. So this is definitely a type of question you may see in MATLAB. And the thing is, if you don't have to do an integral, then you can just try to avoid it. All right. Now let's introduce another concept which is called the average value of a function. Average value of function f of xy rectangle R is given by the following equation. F sub the subscript is ABE, and this is exactly. So if you think about the average value of a function using with only one variable, it's just going to be the area under the curve over the width of your interval, right? But then it's also a similar division. So now you calculate the volume of the solid, and you're gonna divide. And you're gonna just divide by the area of the base. So A of R represents the area of the rectangle. If f of xy is non-negative, then f sub ab f is the value such that the rectangular box with base R and height f m has the same volume as the solid of R and below our surface. So z equals 0. Recall the average of single variable function is 1 over the length of the interval times the interval. All right, so these are the concepts. But now we directly go into the computational method, which is called iterative intervals. So it's a double interval. It's going to be an order, and we're going to show you guys how. So for f of xy, that's non-negative in rectangle R. We learned that volume of solid buffer and low surface is interval. Make sure to write dA. Such volume can be computed from another perspective. Recall chapter 6. volume by size. If the area of cross section perpendicular to the x-axis is A of x for a solid, then the volume is going to be the integral of this A of x dx. And x is actually defined also being the and well, so when I was teaching calculus, I was saying, okay, you have like a football, and then you have the x-axis, and then you have a plane that's screening all the way from one end to the other. There will be cross sections. But here, we're not going to do that figure. We are just going to look at the thing that we've been looking at. So basically, let me go up and I think, yeah, right. So let's just look at this solid. Basically, along the x-axis, you will have a bunch of planes cutting through. So that will be A of x. So let me just sketch that figure while all you guys also sketch. So that's the idea. So it's a surface, and we have and now I have, so this time it will not be huge. Now, okay, so here we have A and B. So they are what? They are the lower bound, upper bound, lower bound for the x value also. And since we are at a rectangular base R, right? So the shape is really nice in the sense that this bottom here is exactly B, and the front plane is actually a plane that's perpendicular to the x-axis, and the one at the back is also perpendicular to the x-axis. Right. So I'm talking about this one. I'm talking about this one in the front and at the one at the back. Okay. So they are already perpendicular to the x-axis. But now if you imagine any plane that's perpendicular to the x-axis, that will be similar. That will be parallel. So you will have something like this. So it's going to be parallel to the y-axis here, and then it's going to be vertical. It's going to be vertical, and this is going to be intersection, which is a curve. And then now this is the cross section, right? For whatever x value that you have, you will get a region like this. And as long as you are able to describe the area of this, that will be A of x. If you for whatever x value, you can describe this A of x, and then you can just accumulate these A of x. That will give you the volume. Of course, the surface is d equals. Now, let us fix x equals some x0. What is A of x? So we intuitively speaking, A of x0 is just the area of the region. But now, actually, it's the area under a curve. So the curve is right here. Actually, I want you to curve like this. So this is the curve. And this is actually a curve, which is a cross section of the surface and the plane, x equal to x0, right? So if you choose x0, let me switch that, it's x0, and this is a of x0, and then this is actually z equals to g of y. Here, x is fixed to be x0, but y is a variable. So you actually get a function in terms of y. So okay, close a look. So now we only look at the YZ plane in this sense, because here x is fixed. Okay, so you have the y and z axis, and then you have a function z equals g of y, and then okay, the y value starts from c and ends at d, right? And then you're looking for the area under the curve. Everything can be pretty bad because we monitoring. Right. So area under z equals g of y, and what's that? That's actually a definite integral, right? So this is actually the integral from c to d of g of y. And from the above figure, we actually know, okay, what's g of y? G of y is actually the multivariable function. We fix the x value. So we can put things together. Let me also show it. So just recall, the volume is the integral with respect to x of a of x, cap a of x. But now cap a is this thing. Okay. So you can do this kind of like a substitution. Please keep that in mind. In summary, v equals the integral. Now we change x from a to b. We are accumulating the area of the cross section, and for whatever x equal to x0, we are looking at the area in red, which is from c to d of g of y dy. And if you substitute gy is actually the function f of xy, and we specify the x value to be x0. And now we can put things together. So we suspect that the volume here, we do the substitution. So if we go along this logic, it's really likely that the volume should be calculated this way. Okay. So here you see, I'm trying to replace this x0 by the variable x, because this that's exactly what's required in the integral. Okay. So this is one way to think about this. But now, if you think about it another way, because this is doing what? This is saying, okay, I'm doing these cross sections that's perpendicular to the x-axis, but you can also do that perpendicular to the y-axis, right? So a similar calculation from a single argument B could be, so if you fix y first, and y goes from C to D, right? And then you're going to integrate something about and then dy, and then that cross section along the y-axis will be the area of the curve. You fix y and you integrate x. So you can see the order of integration is exactly the opposite. And what's the idea? So it's the same surface. I'm going to quickly sketch it. And now we have what we have, C and D. Now here we're doing these planes that are perpendicular to the y-axis. So that's whatever y that you fix right here. It's going to give you vertical part all the way up, vertical part all the way up, and the intersection. So you can say this is d of f of x, y, which is the surface. But then if you have y0 to be this, then this is what this is actually a intersection. That's d equals f of x, y0, right? Which is function of x. So that's why you're equating f of x, y0 on the interval from a to b. This is a right. So actually, it turns out that these both of these equations are true. As long as your function f of x, y is relatively nice, let's say continuous. If the function is continuous on this interval, then definitely it's going to be fine for both ways. But here we are putting question marks because this is actually a really important theorem that it's not really guaranteed to happen for whatever for general functions, but for computer functions, that is true. Okay, so now let's take a look at the integration. The integration is not going to be an easy issue. So now we're given a multivariable function, right? So if you're looking at the process, so this is it's a bivariate function that we're integrating. We are fixing y, and then we're integrating with respect to x. So this is a very important idea. Integral that involves several variables. Recall. Let's say if you have the integral from 0 to 3 of ax squared dx. So here it's just a constant a times x squared, and then you're integrating this. I would say a quadratic function, but it's just the leading coefficient is a. Okay, and what do? So we treat a as a constant; it will be dragged out, and the x squared you just find the antiderivative. Right? So the antiderivative of that, the power rule, so it's so 2 add 1, that's going to be a 3, and we divide by that 3. And I can even make this a to be that. So although it looks like a variable parameter, but it's even unknown, but you know it's a fixed number. Right? So then you can plug in x equal to 0 and x equal to 3. So recall when you were doing Calc 1, you just need the lower upper bound, but you didn't even need to write x equal to something, x equal to something in the indices. But here in our course, we require you guys to write that. Okay? So here this is x. So if you plug in this is 1/3 a times 27 minus 1/3 a times 0, which gives you 9a. So I'm going to mention that if you change a to be just the variable y, okay. So in our particular situation, we are integrating with respect to one of the variables here. This is integrating with respect to x, and y is treated as a constant. So if you have that, it's going to be the same thing. So therefore, I'm going to quickly finish this integral because this is actually exactly the same thing. So I have y, x squared. I do the same integral, so it's still the same idea. So I do the antiderivative of everything in terms of x, but y is a constant multiplier. I'm treated as a constant. X is 0 and 3 in the lower bound. You see why I'm doing this x equal to, because there's another variable that I don't want to mess with. So this is exactly fine. Right. So note that the above integral is a function of y. Hence, we can further integrate it with y on the outside. So this is a function, so then you can integrate that, let's say, for y, where y goes from 1 to 2. And let me put the above function in terms of y in the close brackets. So we can write this down. And then we also know as a fact that the integral in the middle as a result of 9y. So we can integrate it further. And 9y is not difficult to write down the antiderivative because y is power function 1. So the rule of antiderivative is the power rule, so you add 1 in the exponent and divide by that result, which is 2. So it's 9 over 2 y squared. And notice that here, different from what we write down in the univariate calculus here, right here. So when we are plugging in the lower upper bounds of the integral, we are writing exactly what the variable is. So here we have x equals 0 right here, and x equals 3 right here. So that's very important. So because we now have more than one variable, so it's really necessary to verify which variable that you're integrating and which variable that you're substituting. Okay, so here it's y equals 1, y equals 2 for the lower upper bounds, So you're gonna plug in, it's gonna be 2 over 9 times 2 squared minus 2, basically 9 over 2 multiplied by 1 squared. Essentially, it's 27 over 2. Right. So this is an explicit example of how we calculate the iterated integral. Okay? But this is relatively a simple function. Okay, so iterated integral. To be a little bit more specific, there will be a double integral with the 2 variables. But notice that, okay, here for this section, we are defining these integrals on rectangles. If you recall, we have x between a and b and y between c and d. So here, if you're writing y on the outside, this is going to be y from c and d, and you're going to write dy at the end. And now, for a and b is going to be the x variable. The dx is going to be in the inside, dy is on the outside. So we usually write this, but if you really want to be very specific about the order, so dy is on the outside. So you can think about this as saying, okay, I'm gonna integrate the thing on the inside first, which is about x. I'm gonna put the angled brackets to indicate the explicit order of calculation. Okay, so it's going to be the inner part that's calculated first, which is writing x first. And then once you're done, you're going to calculate what's on the outside, which is 1, which is 1. So when you're writing this iterated integral, the different order of the differential part, okay, it's going to tell you the order of your calculation. So usually, if you really think about it, these values at the integrals would not really tell you what the order of the equation is. Okay. But this part, this differential part, will be critical for that. Okay. And of course, you see, this is dx dy, right? So this is another way of writing this dy dx. Then if you write dy dx, then the outer is going to be with respect to x. It's going to be from a to b. Dy dx. Okay. And then the inner is y is from a to b. If you think about the rectangle that we are working on. And then, of course, this is the notation that you write, right? But then if you think about the calculation, if you want to put the brackets, it's going to be from c to d of f of x y dy. You need to calculate this. And here, once again, you're treating this as if your x variable is fixed. Okay, so you're integrating y first, and then for this integral here, you will kill off the variable y, and then it's going to be a function with respect to x, and then you just integrate with respect to x. All right, example. So actually, we have seen this right above. So yeah, let me just circle that. Okay. So we have done one of the calculations already. So if you are doing this integral, of yx squared dx dy, we have the result already from above, which is 27/2. Okay. So what happens if we do the other order? Okay. So if we do the order in terms of x first, and this is in terms of x first and then y, right? So if we change the order, it's going to be from 0 to 3 with respect to dx first on the outside, basically. And then from 1 to 2, dy on the inside, which is the first. Okay, so let's do that first and see if we're getting the same result. Okay. So if we're writing this down, and in terms of the order of calculation, it's going to be the inside that's calculated first. So I'm going to include the brackets again. And then basically, we're just going to copy whatever that's outside the bracket. And then, okay, so dx is going to be here. But then we're going to calculate what's inside the bracket. Okay. And now, for this part, this is the integration about y, right? And then we are treating x as a constant. Okay, so x does not change here. It's going to be just a constant multiplier. So you will have x squared that's not going to be changing. And then now y. Y is only a power function that has a power 1, right? So you just do the antiderivative, which is y squared over 2. And then we're going to evaluate, because here y goes from 1 to 2, so y is at 1 first and then 2. Okay. And then we need to evaluate. So what's on the outside still is kept there. So if we need more space. So we're just plugging y equal to 2 and 1 and do the subtraction. So it's going to be x squared times 2 squared over 2 minus x squared times 1 squared over 2. So you have what? You have 2 times x squared minus 1/2 x squared. It's going to be 3 halves squared. Yes. Okay. And then you see, okay, this is another power function. This is x squared. So add 1 and divide. It's going to be 3 over 2. It's a constant multiplier in the front. And then it's going to be x squared 3 over 3 multiplying. And then we're going to evaluate. So this is the antiderivative, right? And we're going to evaluate as x equals 0 and x equals 3. This is so if you are killing off the constants, this is x equals 3 over 2. Okay, so exactly you are getting 27 over 2 minus 0 over 2. Same answer. Minus 0, which is so now you see in one of the orders we get this number. Okay. If we do another order, it looks like it's the same output. Okay, same result. But besides the order of calculation and the fact that if you are integrating one of the variables, you're treating the other one as a constant. Besides this fact, then there's nothing really. It's really delicate. Okay. Remark. So you see in this example that the two orders actually give you the same result. Okay. So we did dx dy first, and then we did also dy dx. And at least for this function, yx squared that we're integrating on the rectangle that we have specified, the integral is giving you the same result. So here comes the theorem. If the function here is relatively nice, then you actually can interchange the order of integration on a rectangle. So this theorem is called the Multivariable theorem. So if f, the function, is continuous on rectangle R, then larger line, where the rectangle consists of all the pairs x, y, such that x is between a and b, and y is between c and d. Then the double integral on this region R of the function f of x, y, dA. Recall that dA is the area of the base that you're trying to accumulate. So this integral can be written in the two ways, which is giving you the same final output. So you can either write it as dy dx, or in terms of dx dy. It should give you the same result. As long as your function here that your input is continuous. So once again, the order does not matter, but it always has to coincide with your variable integration. So you once again, dy dx. Okay, so dy is on the inside. Okay, so that integral from c to d about y is also on the inside. Very important. Example. So actually, we have calculated from the previous example that these two integrals are the same, right? So you can also conclude that if you are specifying the rectangle for this function y squared, then this integral is definitely going to be the same. Okay? So if your rectangle is 0, 3 plus 1, 2, where x is between 0 and 3, y is between 0 and 2, then according to the theorem above, that this double integral over this region R is going to be the same value, 27 over 2. And we have the double integral of this function y squared over the region R. That's going to be exactly calculated by one of these. We have seen from previous examples that both integrals, both iterated integrals, yield 27 over 2. Another example. So if you're looking at this kind of polynomial function, it should be relatively straightforward. And then no matter which order of integration, if you look at the previous calculation, it's not so complicated. But now, I'm going to give you a relatively more complicated example. So such that the order of calculation actually matters very much. Okay, so now this integral is y times sine of xy dA, where R, the region, is 1, 2 cross 0 pi. Okay. So in this example, I would like to mention that these two orders will be of the different level of difficulty. So just like to warn you, and I would like to mention also before we do this is that the integration by parts will not be actually required in the exams, but the use of fusion is definitely necessary. Okay. So this is just an illustration. Okay. One more thing before we start. Okay, so for this notation, so if you read from this context, what's the range of x? X is between 1 and 2 or from 0 to pi. What do you think? From 1 to 2. I see some of you already answered. Okay, so x is from 1 to 2 and y is from 0 to pi. Okay, so that's the order of this notation. Okay. Solution 1. So let's say we do x first and then y. So of course, this double integral can be rewritten as so if you're doing x first and then y goes on the outside from 0 to pi, from 1 to 2, y sine of xy. Next to it. So basically, if you're looking at this, okay, so this function is actually a function in terms of y. If you think about it, if it's in terms of x, it's actually relatively simple, okay, on the inside, because y is going to be treated as a constant, so you just have multiple sine times something of x, okay, something times x. So that's relatively straightforward. But if you change the order of integration, then it's going to be a little bit more complicated, because if you have dy on the inside, this is y times sine of y, something times y. Okay, so it's a product which is relatively more complicated. Just as a heads up. So this is why we're choosing this first method, that we're doing x first. So just like we mentioned this. So we can on the inside we treat y as a constant, right? So you can drag that out. Actually, although we are doing that first, but if you really think about this integral, you can say one way is you factor this y out. The second way is that you see this is x times y, right? So it's really like a u substitution that you can put y times dx together as du, and you make xy to be the u variable that you want to do this u substitution. So, which is really a typical way of doing this. So let me write that down. Okay. So if you do not factor that out, so alternative. So y sine of xy So here we're integrating with the x. So you can say here u equals to xy. So treating y as a constant. So du is going to be y dx, right? And it is exactly here. Okay. So this whole thing becomes sine of u, du. But notice that here x goes from 1 to 2, and then this u variable will have a different law of the bounds. Okay? That's very important when you're doing the substitution. So these bounds are very important, and you should notice that when let me write it under this. So when x is 1, u is what? U is 1 times 12 is 1. Okay. When x is 2, u is going to be 2y. So we need to change the law of bounds. It's going to be y here and 2y here. Okay. Very important. And of course, now, if we have factored y, then this procedure is going to be exactly the same. Still, either you want to write the antiderivative of the sine of xy, or you just want to do the u substitution again, if you really don't remember what's the antiderivative of this. Okay. So, anyways, so here we have done the u substitution already on the right. So here I'm just going to write the answer directly for the antiderivative. So y, and now on the inside. Okay, so this is treating y as a constant, right? So this is sine, excuse me. So sine, okay. The antiderivative is actually negative cosine. And here, notice that you have y in the front, and you also need to do the division. For the antiderivative. And of course, if you are writing this down, also make sure that you double check by differentiating. Okay? So negative cosine gives you sine as a derivative, and then the chain rule will give you the additional y. Okay. You need to also evaluate. And here, x is 1, 2. Substitute. Okay. So firstly, we have x equal to 2, which is negative cosine of 2y over y plus, okay. We have a minus, but of course, 2 negatives make a plus. Okay. Yeah. However, we use minus there. Because we have a correction. Negative cosine of x now is 1, so it's going to be cosine 1. And of course, you can see that these y's are going to be cancelled. And these two negatives make a plus. Okay. So now you have what? You have negative cosine 2y and then plus cosine 4y. And now you're integrating y. So now you can write down the antiderivative again. Okay. So what's the antiderivative of cosine? It's actually a sine, right? So here for the negative cosine, it's going to be sine of y. Okay. And of course, if you differentiate, you will get a cosine back. But then for the negative cosine in the front, you will have negative sine of 2y, but then you divide by 2. And if you differentiate by chain rule, you have what? You have cosine of 2y times 2 at the derivative of the inner. And here, that's the antiderivative of the whole thing. And then y equals from 0 to y equals to pi. And now you see, okay, for sine of y, sine of 2y, if you plug in pi, you will get sine of pi, which is 0. Sine of 2y, 2 pi is a 0. When y is 0 for both, they are 0. And of course, can do another use of cosine of 2y dy if you need it. And here u is going to be 2y, for instance. And then du is going to be 2 dy. Right? But here we're just directly writing down the antiderivative. And so if you plug in, it's going to be for the first function, it's going to be negative 0 over 2 minus 0 over 2 plus for the second function, it's going to be 0 minus 0 because sine of pi, sine of 2 pi, they are all zeros. So eventually the result is 0. All right, so this is solution 1. Okay. We're following the original order, and we also need to emphasize that here for the inner part, with respect to x, we're doing this first because this function, if you look at this function of x, is much more simpler. Any questions? So once again, very important, U substitution. Okay, so now we see U substitution once again. Very important in this chapter. And it's definitely required. Any questions? All right, now let's look at solution 2. The other order is a little bit more complicated. Solution 2. Okay, now this double integral over the region R of y sine of xy dk. So let's put x on the outside. It's from 0 to 2. Is it from 1 to 1 to 2? And from 0 to pi y sine of xy. X. Okay, now if you're looking at here, this is a function of y on the inside, which is y has a sine of x. Right? So this is a product. So how do we handle the product? It's going to be equation parts. And if you really think about the trick of integration by parts. Yeah, let me write down the bracket here also, just to specify. Okay, we have to look at this inner part, right? First. And then what about equation parts? If you recall, there's a rule called what IDEX. So it's inverse trig, a logarithmic, algebraic, trig, and exponential. Okay. If you recall, and if you're looking at here. This is what this is now. Which is value y, right? This is a trig, and y is actually an algebraic. Okay. So here you see you have algebra, you have trig, So the algebraic, this is the higher on the list, so it will be the U, okay? And then the rest of the thing will be dB. Let me put it in red. Here, if we integrate y sine of xy dy, so probably in Calc 2 you have done it in a relatively different notation than it's actually either way is fine. So if you want to write everything on the right hand side, or if you are writing everything above and below this equal sign, it's either. Okay, so U is going to be y, dV is going to be the rest of the things. So it's sine of xy dy, and then you need to do what? You need to do du, which is dy and v. Here you need to somehow finding the antiderivative, right? So sine of xy in respect to y, what's the antiderivative? It's going to be negative cosine xy over x. And if you differentiate with respect to y, you should get sine of xy times x over x. Okay, that's over. Okay. So this becomes what? This becomes now this is that you can say direct substitution. Okay, so y is replaced by u. Okay, so the rest is replaced by dv. Okay, and then integration of parts tells you this equals uv minus the integral of vd. Integration by parts. Let me put P in capital letters and substitute. Okay, just so uv, so u is y, v is negative cosine of xy, 14 over x, minus, and v is negative cosine of xy, 14 over x, but du is dy, which is nice. And now, if you're looking at this part, this integral is much simpler than the previous, okay? Because the previous one is this. This is sine times a sine of y times y, right? You have a product of functions. But here, although this looks like a fraction, but x is now treated as constant. Okay, so you have only a cosine of something, which is much simpler. So you can now either substitute everything back in here, or you can even explicitly write out what's the antiderivative here. So let's do that. Let's write out what this is. So the beginning part is still that it's negative cosine y times cosine of xy over x. And now here we have what? We have a plus. Let's make it a plus. Now, what's the antiderivative of cosine? Sine, right? Sine of xy. Okay. Now this is once again a function with respect to y. Okay. So you need to divide by x because of triangle. Also, make sure to verify if you differentiate. So it's going to be cosine. If you differentiate with respect to y, it's cosine of xy times x, and then dividing by x squared. That gives you that. Any questions so far? integration by parts. So I would like to once again emphasize that this is integration parts is not really required in that, but you need to be there's no how to handle this because it may occur in MATLAB questions. Okay, let's do the substitution. Here we need to evaluate that. What's it? 0 and pi. Okay. That's fine. Hence, integral from 0 to pi of y sine of y is going to be this function negative y cosine y over x plus sine of xy x squared evaluates as y equal to 0 and y equal to pi. Okay, so we're plugging. So we have what? We have negative pi cosine of pi x over x plus sine of pi x over x squared minus. So here we have negative 0 cosine of 0 over x plus sine of 0 over x squared. And you see, for those zeros in the negative brackets, they're just going to be zeros. Okay, the sine of 0 is 0. The 0 in the front is a 0. So this result is just a little complicated in terms of x, because we see products once again. Right. So that's the result for the inner bracket in red. Okay, in the above. If you're looking at this integral right here, we still need to do the definite integral with respect to x from 1 to 2. Thus, from 1 to 2 of the integral becomes from 1 to 2 of the function above that we're integrating. X and let's isolate these two integrals. We'll have what? We have negative pi times integral from 1 to 2 of cosine pi x over x. Yes. Plus the second integral is about sine x over x squared. Yes. So now these both of the integrals looks really complicated, but if you really think about this kind of product, I would say the integration by parts is probably the only way that the only way out, because although it looks relatively complicated, but it may relate to the other integral right here. So let's treat the first integral. Here, if you're looking at cosine of pi x holding over x dx. So this is again an integration by parts. Once again, this part, this is the algebraic. This part, this is the trig. And the algebraic is not x. The algebraic part is 1 over x. That's very important. U is 1 over x. dv is everything left behind. When you're doing integration of parts, it's always a product. Okay, so du is going to be so 1 over x, the derivative is negative 1 over x squared, yes. And the energy for v is going to be sine x over pi. And if you differentiate, it's going to be cosine pi x times the derivative of the integral, which is pi. Okay. So now do the substitution right here. So 1 over x is u. The rest of the thing is dv. So it's going to be uv minus v du. So uv is sine of pi x, whole thing over pi x minus v du sine pi x whole thing over pi. And du we have negative 1 over x squared dx. And let's simplify a little bit. So sine of pi x whole thing over pi x. Now, if you look at this plus and plus, we have sine pi x over x squared. Okay. So if you look at this, very similar. Okay. So this looks exactly similar to the circle term in the above integral. Okay. And if you're looking at the common factors 1 over pi right here, it looks like this integral will lead you to a negative of this. Okay. So that will cancel out with the thing here. So that's what we are going to do right now. So negative pi over cosine pi x over x, the integral, plus sine pi x over x squared parts will become substitute. So we need the substitution. Sine pi x over pi x. So here we evaluate at x equals 1 and x equals 2 plus 1 over pi. Here I'm doing a substitution, but I still need the negative pi in the front for the multiplier because it's the second term. And from 1 to 2, sine pi x. So this is just a substitution that I have done for the integral parts. And then I add from 1 to 2 cosine pi x. That's good. And notice that these two are flexible. So although sine over x squared, this is complicated, but they are infinite. So now we only have the substitution right here. So this is negative pi. Plugging x equals 2, you will have sine of 2 pi over 2 pi minus sine of pi over pi. And as a fact, you know, sine of pi, sine of pi like that. So from this example, you see, eventually you will get the same answer. Because once again, the function that you're integrating is actually continuous. But the different method is definitely different, different level of difference. So you know, solution one is apparently easier than solution two. In practice, it is wise to choose integration order that gives simpler results. So now more examples. So let's look at example. Find the volume of solid Fs that is bounded by the elliptic paraboloid x squared plus 2y squared plus z equals to 16. The plane x equals 2, y equals to, and the other plane y equals to 2. So probably I want you to say the paraboloid, the planes, and the 3 coordinate planes. Let's firstly take a look at the shape in the geometric sense. So firstly, of course, it's an elliptic paraboloid. What does it mean? Basically, if you fix x, it will get you a parabola. If you fix y, it will get you another parabola. But if you fix z, you will get a ellipse, right? And then basically, when you fix the x or y, then you see this is actually a parabola. These are giving you a parabola opening downwards. So we should be familiar with this kind of shape. So it's actually going down. Okay. So if you fix z, it's going to be an ellipse. Y, x, z. Yeah. So let me get a little bit more space here. Okay, so basically, so that's the surface on the top. which is x squared plus 2y squared plus z equals to 16. And now, okay, we have planes that are vertical. So x equal to 2 is let's see. So the maximum x value in the xy plane right here should be, excuse me, that should be a 4. So basically you set y and z to 0, you will get a 4 here. Okay. So if you fix x and z to be 0, you will get what? You get a 2 square root 2 right here. Then that's your equation. Right. But now we have a plane that's vertical, so x equal to 2. So that and y equal to 2, that also goes into this solid, right? And finally, we have the 3 coordinate planes. So basically we have what? We have this plane right here. So that's the xz plane that's cutting off the left hand side, right? And if you have the yz plane that's cutting off the back, okay? So we only have the front and the right hand side and the piece that's above the xy axis. And at the same time, we're cutting off here y equal to 2 is somewhere just in the middle. So probably here. So it's cutting the right hand side. Okay, so this is y equal to 2. And then we have x is 2, so that's another vertical thing. So x2 is here. Vertical be up. And then this is from, yeah, so upper bounding curve. Right. Now, basically, there's an intersection right here, which is 2, 2, 4, 0. And basically, we can just plug in to see if this 2, 2, 0 is within the solid or not, right? So basically, 2 squared plus 2 times 2 squared plus 0 actually is 4 plus 8 is 12 less than 16. Okay. That tells you, okay, this corner right here is actually within the ellipse at the bottom. Okay, so that tells you, okay, this solid exactly is what. So at the top we have the surface. Okay, so that's the elliptic paraboloid. But then the left hand side and right hand side are cut off by the vertical planes. The front and back are cut off by the vertical planes. And then the bottom is the horizontal plane, the xy plane, right? So this is exactly the shape where on the top we have a surface, but then in the front we have, so this is y equal to 2, so this is x equal to 2. On the top, we have x squared plus, well, of course, we can rewrite it so that z is 16 minus x squared minus 2y squared. Right? So this is the functional expression in terms of the solid. And if we want to fill up the transparent figure, so that's it. So x-axis, y-axis. So this is the solid we're looking at, right? And at the bottom we have the rectangle. Right? The x equals 2, right? Right? And now we just simply set it up. So basically, we are sure that okay, the bottom region is the rectangle, so that we are able to simply set up the volume equals to. That we go over this region R, which is the rectangle where x is between 0 and 2, y is between also 0 and 2. And then we, the top is actually the function 16 minus x squared minus 2y squared. All of a sudden it's crashed. Okay, but everything is still there. 16 minus x squared minus 2y squared. Okay, so that's the functional value. And of course, the bottom is 0, so we don't really have to minus that. But then we accumulate. Okay. So any questions so far? Okay. Just basically this is the volume of the solid under the surface at the top. Okay. All right. Now let's this function here is relatively nice in the sense that it's just a polynomial function. So I would say integrating it by either direction is fine. Okay. So let's just quickly do this. So here basically x goes from 0 to 2. Y also goes from 0 to 2. So here let's just do dx dy. Okay, so we integrate x first and then y. Right. So since this is actually like what the second example, right? So just now we did one in the quiz, but now let's quickly do this. So basically, when you write dx dy, that just says okay, you integrate x first, while you're treating y as a constant. That gives you 16x minus x to the 3 over 3. So that's simple power function. So you can do the power. So minus 2xy squared. So this is the antiderivative in terms of x, right? If you differentiate with respect to x, you should get the same function back. And then plugging in x equal to 0 and x equal to 2. Finally, once you get that result, just integrate with respect to 1. So anyways. It's so here we notice that if you plug in 0, you just get a 0. So the only important evaluation is at 2. So it's 32 minus 8 over 3 minus 4y squared. Okay. And now we integrate with respect to y. So that's not going to be complicated to this situation. So we introduce y here and y here. So now we have y squared that gives you y cubed over 3. Whenever you do an antiderivative, always quickly differentiate in your mind and see if you get this inner function back. The function that you're integrating. So now evaluate y equal to 0 and y equal to 2. So once again, 0 doesn't give you anything. Okay, so evaluate 2. So 64 minus 16 over 3 minus we have 8 4 times 8, that's 32 over 3. So this is exactly 64 minus 16, which is 48. So it's good. Okay. So for this kind of polynomial function is always not so complicated. Okay, but if you have more complicated functions or even products, then it will get messier. So that's what makes this 3 worse harder and harder. So now more examples. So this is actually the last one, but we can do it pretty quick. So let's say the region now is once again from 0 to pi over 2, multiplying, or you can say crossing by the equal from 0 to pi over 2. But then this cross is just a notation, okay? It doesn't do anything. So we want to calculate the double integral over this region R of sine n times cosine phi. Yeah. So here, this is actually a nice function in the sense that this is a product of two individual functions in terms of x and y. Okay. So these functions don't really mix with each other. So this is a really nice situation because eventually we will see that we can separate the integrals into two pieces. Okay? So here let's just write out the integral. So let's say we do dx dy. So here the interval from for y is from 0 to power 2, and for x is the same. And then sine of x cosine of y. So here, if you are looking at the inner part, that's enclosed by a bracket. So here, when you're integrating x, right, then the y part, this function is constant and it's a multiplier. So we know that we can take it out of the this integral. Okay. So what we get is from 0 to power 2, cosine y is taken out of the brackets, and then on the inner we have only the integral in terms of x. Okay. So what's good about this step? So that's straightforward, right? So this cosine doesn't do anything in the integral, so we can take it out. But now we can do the same trick because this is a constant number, right? So the integral in terms of x only, that's constant if you calculate the definite integral. So this is something that we can take out of the integral in terms of y as well. So that tells you, yeah, let me write it down. So this is a constant. So that tells you this equals to, so we can take that out right here, sine x. And then what remains is the integral only in terms of y. Okay. And now, so the integral for sine and cosine on the interval from 0 to power 2, they're both 1. So eventually you get 1. Okay, so make sure to evaluate, verify that. But then let me quickly write down the remarks for this situation. Basically, if you have the domain as a rectangle that's bounded by from A to B and from C to D for x and y respectively, then the double integral for function g of x times h of y dA. So here you can separate the integrals into pieces. So you can just accumulate x for g of x from A to B, multiply by the integral where you accumulate h of y from C to D. Okay, so that's actually a nice result. Whenever you see a product, you can separate the integral. Okay? So that's pretty much it for today. So let me end your recording.